All right, everyone. I am on the line with Beidi Chen. Beidi is a PhD candidate in the Department of Computer Science at Rice University. Beidi, welcome to the TWIML AI podcast.
Thanks.
So I had the opportunity to hear Beidi's presentation at the systems workshop. ML was, I always get confused. ML for systems, systems for ML. This was systems for ML, correct?
Yeah, they changed the
Yeah.
name recently too. We submit this paper to the conference. They first have it called MLSys, and then
Uh-huh.
they later change it to SysML because of the trademark stuff.
Yeah, well, I think there are
Workshops there.
multiple different workshops with very similar, with all the same words, but in different orders.
Yes.
But in any case, you presented at the workshop on your paper slide, which we will go into. But before we do that, share with us a little bit about your background, what sparked your interest in machine learning, in particular on kind of this intersection of hardware and algorithms. How did this all come about?
Sure. So before I studied my PhD at Rice, I had my undergrad in University of California, Berkeley, and I was actually doing some networks research. It's kind of still computer science, but a little bit irrelevant. But that kind of, yeah, that actually increased
I
my
did my
interest.
grad work in networks also, like stochastic modeling and all that kind of stuff. Is that the
Oh, that
stuff you were doing?
no, not the same.
Different kind of networks?
Yeah.
Okay.
Yeah, so we're kind of doing like a software-defined building. And
Oh, okay.
yeah, so that was kind of close to the AI part because you want to automate some process and you want to predict
Oh,
something for people. Yeah.
okay.
Yeah, then when I come to Rise, I got interested in the machine learning algorithms because I thought I always have this in mind. All the problems we're trying to tackle in computer science, not all, like most of it, the bottlenecks are usually the computation. Not all
Hmm.
the problems are showing this part, but if you think about it, we usually have a brute force way of doing things. And if we do have the computational power or we have the time to achieve it, then the problem solved. But the problem is we usually don't have that time and computational power.
Hmm.
So for the algorithm part, what is good is reducing from big O n squared to big O n or big O n to constant is usually making that possible. So the way I'm doing research is kind of I always think about what is the brute force way, what is the naive way I can chip this, and can I speed it up,
Hmm.
either in time wise or reducing the memory, any part that is blocking this happening to produce the optimal solution, and we can do approximation. And that's why I kind of doing all the randomized algorithms in my PhD because that's gonna help
Okay.
with the memory and time.
Meaning the algorithms are take advantage of randomization, or you just are working on a bunch of random different projects?
That is also true because we're using our special weapon, this randomized algorithm called locality-sensitive hashing, all kind of applications to tackle different problems.
Got it.
Both.
Got it. Got it. Got it. So this locality hashing is kind of, well, obviously at the core of the paper you presented at the MLSys workshop
Yes.
slide. What is the full name of that paper?
Let me see. We changed a bunch of times. And I think the first version, we're trying to saying that we're defending for the smart algorithms over specialized hardwares. And then
Mm.
we found it kind of offensive to some people because we're not saying hardware development is not good. We're just saying that we also need more progress on the algorithm side. So we're just changing the name back to we're beating, like side trying to beat GPU over like CPU stuff. So it's like the
Okay.
result of the paper. So they'll,
Nobody gets offended
yes,
by
nobody.
GPUs beating up on CPUs except Intel, right?
Yeah, we actually have three more collaborators after the first version of the paper came out. They also help us further speed it up and by using all those Intel tricks.
Before we get into the kind of the core innovation of the paper, what is the motivation? You've hinted at this also.
Yes.
Everything takes too long, but maybe talk a little bit more about the specific problem that you're trying to solve with this paper.
Right. So we all know that now all the applications like vision, NLP, and they all kind of have the state of art by using the neural networks. But the problem,
Mm-hmm.
one bottleneck of the neural network is the computation. That's why the inspiring GPUs were invented, and then people have the computational power to kind of do this all complicated computations. So the major bottleneck is still the matrix multiplication. And if you can do like large matrix multiplication really fast, then that's kind of solving half of the computational problem in neural networks. And that's why we started from those. The problem, which is like called extreme classification. So basically, for example, you're an Amazon user, so you're typing something like I want Nike shoes, and then in the backend, hopefully you're gonna have a black box, which can help you decide which products to show to you. Then
Mm-hmm.
this kind of reduced to like extreme classification because you are typing a query. Does your query belong to for 1 million classes? Which one is it? One class can be Adidas shoes. One class can be like Nike running shoes, stuff
Mm-hmm.
like that. So for this kind of problem, the major computation is the last layer because you have 1 million classes.
Mm-hmm.
Then you have to do all this the major computation over there. And then we're thinking about is GPU the only way to solve this problem? And because we realize for this kind of problem, even GPU, the speed up is not enough because like the high memory access.
Mm-hmm.
And then we're thinking about are all the computations necessary? Then the answer is actually no, because majority of it is redundant. Because
Mm-hmm.
in the neural networks, if like the hidden layers, usually you care about the high activations, which is like to inner product producing high results. And for the last layer is like even worse because for those kind of extreme classification, what you care is about Nike shoes, Adidas shoes, but you don't care about a headphone. So
Mm-hmm.
that's those irrelevant stuff, like the computation is kind of wasted. But the problem is before you do the computation, you don't know which part are important, or which part does not.
Right.
And then the hashing algorithms is exactly good for this kind of situations, kind of predict which computation are going to give you like high density so that you just compute those to do approximation of the for the full computation. And then in this way, all the computations in the neural networks will be sparse and including the backwards. So that's how we come up with the problem and find the solution.
So you mentioned hashing algorithms are useful here in telling you which of your computations are going to be useful. Why and how is that?
Because usually locality-sensitive hashing is very useful for the search or ranking industry. The reason why is it's good for finding the nearest neighbors. And
Got it.
in the neural network space, what is near neighbors is like if two vectors tend to have the similar direction, then the inner product will tend to be higher. Let's assume a uniform norm here.
Mm-hmm.
So in this way, vector A and B are neighbors if they can produce high inner product.
Mm-hmm.
Then hashing is kind of if you know vector A, we can spend constant time find all the B's which are close to A, neighbors of A, and producing those B's which has the higher inner product with A. And that's why I call it like a useful algorithm exactly for this kind of situation.
Got it. Got it. So locality sensitive hashing, that's something that has been around. That's not something you created.
Yeah, that has
It's
been like 20 years or
been
so.
around for 20 years. And, what are some of the other applications in which it tends to come up? You mentioned search.
Yeah. Usually, so for locality-sensitive hashing, one big application is if you have, let's say, 1 million images or
Mm-hmm.
1 billion images, you can, and then you have an image of query on hand, for example, a cat. You cannot search linearly for the 1 billion images in a database because that's gonna cost
It'll
you
take a long
big O
time.
N. Yeah.
Yeah.
So the only smart way is you save the 1 million images based on some kind of structures, which we call it like neighbors goes to the same bucket, so that whenever you have a query, they will quickly use the same way to compute the hash code and go to the bucket which contains all the neighbors, so that your search time is big O1. Otherwise, when you type something on Google, it's probably take you ages to search for all the information currently we have now. So we have to reduce this search time to big O1 instead of big O(n). And that's all the hashing algorithms are used for.
Producing the hash, is it kind of a deterministic process, or is there a formula, or is it a learned process? Are you learning the hashes across the data set?
So there are two categories. One is the learned one, and we're actually on the other side is like data independent. But the hash functions are not deterministic. It's drawing from some distribution, and all the hash functions are only guaranteed that for example, you have two items are exactly the same, and then the probability that searching that element will be 1. But if the element has some minor differences, then the probability will be different. So by calling probability is each time you generate the hash function is probably different ones. So we can only say that is with high probability, we're going to retrieve the neighbors.
It seems like if the hash function is going to determine the proximity of different pieces of data, it needs to know something structural about the data. And I'm wondering then, does that mean that, you have to do a lot of work up front to, create this hash function based on a given data set? And then, anytime you want to look at a different type of data, do you have to redo that?
No, but we actually provide the freedom for users to implement their own hash functions. So there are 4 things we're providing for different kind of similarities. I think for hash functions, there are 2 lines of work. The first one is the learned hash functions. We're currently not going to that line, but people have freedom to add in those solutions to our framework as well. But the second one is we're focusing on the data independent one. By data independent, I'm saying that not only based on the data, but also based on different similarities. For example, the most useful ones in our framework currently is cosine similarity. I was just talking about if you want 2 vectors to determine which vectors are around one query vector, then cosine similarity might be the most useful one because that's kind of determining the angle, which is the direction. And another one is like the ranking. So they don't care about the norm of the vector or like the sequence of the vector, but they care about the rank. Like for a given vector, the first one, the first dimension is larger than the second is larger than the fourth. Like this kind of preserved order, that's extremely useful for images. And there are a third one, which is called min hash, which is kind of preserve the Jacob similarities. Like for 2 given set, is preserve the similarity between it. So it's actually for different similarity and different kinds of data, you can use different kind of hash functions to achieve the same guarantees. And I'm recently also getting into the learn hash function, that part. But the one particular problem that is extremely trouble our framework is our framework is not we're going to change the hash functions or rebuild the hash tables once in a while because we want to preserve the randomness. But the rebuilding part for those learned hash functions will be very long. Yeah, so that's a good thing about the data independent hash because it is not time consuming.
But the interest in the learned hash functions is that they might be more accurate or allow you to express different types of similarity.
Yeah, that is correct.
Yeah.
That's why we are seriously consider this case in our framework because our framework ultimately wants to spend very less time predicting which neurons should be active and then do all the computation on CPU. That's actually a very hard task. You have to do it very quickly. Otherwise, that overhead is going to kill you.
Mm-hmm.
So that's why I'm talking about like for the learn hash function, although it's very accurate, it's going to help us like spend maybe 10 times of the current time of computing the hash functions. And that's going to make the framework maybe comparatively okay with GPU, but not obvious speed up. So the solution is doable. It's just I think there's a time and accuracy trade-off here.
Yeah.
But we think the independent hash functions are along the sweet spots.
And so what's the relationship between the hash function and the idea of adaptive sparsity? That's a concept that you mentioned in the paper.
Right. So just considering the random dropout is actually like each time you're just giving sparsity to the neural network randomly, so that it's highly possible that you're going to miss some important parts if you do that randomly. So by adaptive sparsity here that's why like for the random dropout, the sparsity can maximum goes to like 50% or so. Otherwise, you will decrease your accuracy. But we do another experiments, and it's actually found in a lot of like previous papers too. If we can compute all the computations and we only take maybe 5% or 1% of nodes as of the active nodes, then the accuracy will not drop. But the problem is you have to make the huge computation to know which ones we're going to produce you the top ones. So that's inspiring us. Like we do approximate like 5% or 10%. But so the speed is kind of close to the random dropout. But the effectiveness of it is close to the adaptive top K. So that's why we find the sweet spot in this too.
Does that mean that you're applying the location-sensitive hashing in two places? One at the very end for your classifier, and then also more deeply in the dropout?
So dropout is actually in parallel with our framework. I'm just giving an example of how the hashing is going to help. If hashing is doing random selection of the nodes, is exactly the same as the dropout.
Ah, okay.
Yeah.
Got it.
If is computing the real top K, then that's called the adaptive sparsity. But it's somewhere in between. It's using the same time. It's very efficient as the random dropout because the query only take bigger one time.
Right.
But it's gonna retrieve you the nodes that is highly possible in that top K. So I'm just like giving an intuition of what hashing was selecting. It's nothing but just selecting adaptively the active nodes for each layer. So what is very useful in the case of extreme classification is because of the full like the majority of the computation is in the last layer because of the number of classes. So that's gonna reduce a lot of computation. But for the usual fully connected neural network, each layer we can build different hash tables, and we can do its sparsity over each layers. So that's not restricted to the last layer.
Are there other elements of this approach that we should be sure to cover? There's the application of the hashing. Do you have to do anything special in terms of your data collection or preparation, or should you just be able to apply this technique?
So we're actually exploring two directions of extension to this work. So this is our current framework support the fully connected neural networks. But people are more interested in when they have like the NLP or vision problem, they want the CN or LSTM. Currently, what we can do is, at least for last layer, we can apply the same technique. But the problem is for CN or LSTM in the middle, like those hidden layers, we have to investigate there to see what advantage is the hashing approach. And for another line of work, we're thinking about the distributed. Because it's well known that for the distributed setting, the computational bottleneck is the communication.
Hmm.
And our slide has its natural advantage here because we're only selecting, for example, 1% or 5% of the active nodes for each layer, so that in the back propagation, the gradient updates is also very sparse. So that
Hmm.
for the distributed setting, this is natural, very efficient.
For the same reasons that we've talked about previously, intelligently using the hashing to kind of identify and strip out the sparsity.
Yeah.
How have you kind of measured the results and compared this approach to others? And then what kind of results have you seen?
Yeah, for the results part, that's the most impactful part people care about.
Uh-huh.
For GPU comparison, we're using the current state-of-art framework TensorFlow, and also run the same program on V100 GPU, which is currently kind of the state-of-art people use to run to perform all the experiments for those applications,
Mm-hmm.
and also for TensorFlow CPU, we also try to see that for all those CPU tricks they're using, are we beating them? And obviously, it will be slower than the TensorFlow GPU, but we still do some comparison there to see like there's 3 lines, which ours is the most efficient, and then TensorFlow GPU on V100 and the TensorFlow CPU on the same CPU machine we're using, because we want to still compare with the CPU. Otherwise, we can use a super powerful CPU machine, and then using that to beat the GPU is not necessary for people, because we want people to do the same thing on CPU, which is not that costly as using like a V100 or this
Mm-hmm.
kind of expensive GPU machines. And also, there's a nice finding about how many cores we include in our CPU computation so that we can beat the TensorFlow GPU. It seems like 8 cores to 16 cores is enough to outperform the same task of on GPU V100. So although we're in the paper, we're using like a 44 core machine, but
Okay.
we do the obligation study to see where it intersects the performance. It's actually 8 to 16 cores, somewhere in the middle.
Okay.
So we
And so
don't.
with
Yeah.
8 to 16 cores, you're able to what? Outperform TensorFlow
Yeah.
on a GPU?
Yes.
Okay. What's the problem that you're benchmarking this on?
Those are extreme classification tasks.
Oh,
Yeah.
extreme classification. And can you talk a little bit about are there established data sets and benchmarks for extreme classification? Can you talk a little bit about those?
Yes. So there's a whole repo about all those. For example, the example that I gave earlier for Amazon
With
data is
Amazon?
usually like, yeah, you have query and you have all the products. That's like extreme classification. Or sometimes you have a user typing query and then you have a search results for the website you are clicking. That's like another case. Yeah, so all those benchmarks are including one repo, all the extreme classification field, like people use those as the benchmarks.
For the Amazon, you said how many classes are there?
For the dataset we're using is 670K.
Okay. And then use another delicious data set that's like the one where you're predicting links.
Yeah, it's like 200K.
So you've got a first set of diagrams where you've got the 3 lines, and that one is looking at the slide accuracy, and then you have time on the bottom. What is the time? Is that like convergence time,
Yes, like training
like
time.
training time?
That's log scale.
Yeah. Okay. So you've got pretty strong results here. Have you had anyone take this and implement it in practice, kind of in industry or for a kind of a live application?
Yeah, I received a couple of emails requesting we have a license there and then people can implement it. And Intel was extremely, of course, they will be super interested in this. Yeah, they're working on it to include to their some kind of libraries in the future too. There's one thing that I want to share. So all the speed ups we're getting here is not about all those C++ or implementation tricks. We don't even use CoolBlast or this kind of libraries for speeding up the computation. We just use all the primitives and all the computations we're saving here are because of the smart algorithms. So because we're only choosing 5% of the nodes, active nodes, so that the computation was saved. So I think this framework, if viewed like we can have further speed up if those techniques, tricks are applied to this. But this is just like a prototype which proves that we can do this with smart algorithms.
Kind of going back to the results, you found that I found the number here, the convergence time required is over 2.5 times less than with TensorFlow GPU. And then I was looking for your accuracy number here. How does it compare in terms of accuracy?
There's no accuracy drop.
Okay, so you're able to maintain accuracy, but converge more quickly.
Yes.
So you've done your benchmarking for this extreme classification task, which has inherent sparsity to it. Are there other types of problems that you think that this would easily lend itself to due to because they also have high degrees of sparsity? Or do you see this as, are there ways to kind of adapt this approach so that you can apply it to use cases where they're not quite as inherently sparse?
So you're talking about the approach we're having?
The approach you're taking and the applicability and, what are the requirements of the scenarios in which it would apply? Do they have to be as sparse as the extreme classification task, or can you see some ways that they can apply more broadly?
It can be applied broadly as I just mentioned. For example, we're currently working on if we can use this speeding up on the training of BERT, which is very popular recently. So the difficulty of applying this to an existing framework is we have to profile where is the computation bottleneck, because speeding up the non-bottleneck won't help. And because we're producing some overheads as well, and that's not gonna speed the whole process up anyway. So we have to find the bottleneck of the training, and if this technique needs the sparsity. So if we do an experiment saying that we're replacing our algorithm with like the real top K and it's decreasing the accuracy too much, then it's not worth investigating. But if we're for example, choose the real top 5% of the active nodes and the accuracy still maintains, then in this case, there's hope for us to do this approximation, because like the kind of like the ground truth works, but now we just need to speed it up. Yeah. So it depends. Yeah, it depends on the architectures of the network, and
So it's not something that you would envision ever being kind of a generic tool in the toolkit that you would apply to different types of problems. You have to kind of hand tailor the application of this technique to the different algorithms and where they're bottlenecked.
Why I think this is still generic is because in all those neural networks or architectures, it anyway reduced to the matrix multiplication problem. Once that one is there, this should be useful. But it's just like we need to see where does it worth it to apply to.
Okay, got it.
And we're also looking for like a GPU implementation of the same method as well, because the major bottleneck for this technique currently going to GPU is because of the hashing algorithm. Because for those many years, hashing only has the CPU implementation because it requires a lot of memory. Because it's remembering something, right? We save something in the hash table. And recently we see a step forward to the dynamic hash tables and GPUs from UC Davis folks. So for those, I kind of foreseen that it might be possible to implementing like a locality-sensitive hashing on GPU, and then this can further speed up GPU, and that's like also a possible future direction of the framework.
Awesome. Well, Beidi, thanks so much for taking the time to share a little bit about what you're working on. It's very cool stuff.
Thanks.